So we're starting a few minutes late, but in any case, welcome everyone to the RASC Halifax Center meeting. We have some exciting stuff going on today, so I'm glad you were able to join us, not only those of you here in the room, but also those of you out in Zoom land. To our new members, or those that have just rejoined, welcome. And to our longstanding members, glad to see your faces here in Zoom. One thing I will ask is that if you have a cell phone on you, please move it to airplane mode or to vibrate only so that it doesn't interfere with our speakers. So thank you on that one. The back one, please. Thank you. Want to acknowledge Tony McGrath, our president, who is here in person today. You'll hear from him later this afternoon. And he can be reached at president@halifax.rasc.ca. We certainly, you can contact us at halifax.rasc.ca. If you have any questions or concerns about the center, please do contact us. We need to hear from you. And also, if for some reason you have to geek out of today's meeting and you didn't hear all the speakers that you wanted to hear, you can certainly see today's recording in the next few days online, and certainly all our previous recordings are on our YouTube channel. So please feel free to join us there. Okay, thank you. We have an Indigenous land acknowledgement to make, and we do want to acknowledge the RASC Halifax Center. Thankfully acknowledges that we live and observe in the unceded territory of the Mi'kmaq people. And also, as Helen Sawyer Hogue said, one of our illustrious long ago members, that the stars belong to everyone. And consequently, we do have an inclusivity and diversity statement that says anyone with an interest in astronomy is welcome to join us. So our agenda today, Dave Hoskin, who's usually our MC, is unable to join us in person. So I got seconded early this morning to fill in for the dear soul, but he is here. I think you can see his face there on the screen. So I'll do the welcome, and then he will do the photo montage and talk about the ETU guides. Then we have Dr. Luigi Gallo to talk about the XRISM. Learned how to pronounce that this afternoon, about his X-ray observatory. Really excited about that. We'll break briefly for a break for about 15 minutes. And then Paul Heath will address his latest poem called The Glorious Rising. Then our president, Tony McGrath, will talk about news from the board and what's new with them. And then Dave Hoskin, as our observing and our education public outreach chair, will address the what's up for October. Okay, so I will hand it over to David. So David?
Good. Share my screen. All right, can everyone see that?
Yes, yeah.
Perfect.
Photos of the lunar eclipse are David's.
You'll get another peek at them in the montage. So we got a fair number of images to see from September. We had a few good nights and a partial lunar eclipse. So lots of good photo opportunities. So Jerry Black took this picture of the waxing gibbous moon at the barbecue at SCO. We had lovely weather for that barbecue. And Jerry also grabbed this shot of Messier 7, Ptolemy's cluster. And this was the, I guess, the debut of the collimated SCO Schmidt-Cassegrain hyperstar. And you can see Jerry got a really nice picture of this open star cluster. And that instrument is available for folks to use when they go to SCO. Judy was busy at the barbecue, sketching and observing lunar features, and she grabbed a few cell phone pics. So this is the Aristarchus plateau, and you can see the bright Aristarchus crater, the brightest on the moon, I believe, and Schroeder's Valley. Nice features there. And this is Mare Nubium with the diamond ring. So Gassendi crater appearing as a diamond ring. Comet C23A3 was visible in the morning sky earlier in the week. And this pic was snapped by Barry Burgess. We're hoping to see it in the evening sky by the end of next week. So keep your fingers crossed. Also from Barry Burgess, the harvest moon on the 17th of September, rising above some trees and water. David Chapman grabbed these images of the partial lunar eclipse on the 17th, so just following the rising of the harvest moon. And on the left is the penumbral phase, and on the right is the maximum partial eclipse of the moon. So you can see the upper northern hemisphere part of that's obscured by the Earth's shadow. And Dave also took a picture of the starry sky and Milky Way at Skull on a September evening.
I don't think I took that. I don't think.
And Jason Dane, this is one of the better images I've seen of Comet C23A3. Grabbed in the morning. He had really nice skies, nice tail on that comet. Hopefully it survives its passage around the sun.
Yeah.
Jeff Donaldson's been doing some deep space object imaging. This is the Dumbbell Nebula, Messier 27. So this is a work in progress from Jeff Donaldson, the Great Lacerta Nebula. It's looking pretty good. Be interested to see what the final image looks like. This is from Tim Doucette, the waning crescent moon and the comet. So nice earth shine and reflection in the water, some ground mist, and there's the comet in the right-hand corner. Very pretty morning shot. Lisa Fanning grabbed this image of the waxing gibbous moon, 14th of September. And she also captured this image of pre and during the partial lunar eclipse. Paul Gray's been, in addition to doing a bit of sketching, has been took this picture of Jupiter, and you can see the great red spot just coming into view. I snapped this picture of some solar prominences on the 13th of September. It's really a nice display that day of the sun. And this is a white light image of the sun yesterday, and on the right, this is sunspot group AR3842, which is the sunspot that's been responsible for the coronal mass ejections, which may give us some good northern light displays if the sky clears early morning tomorrow or tomorrow evening, depending on when they arrive. Quite a big sunspot. And we had a period of good seeing. I was able to get this image of Saturn.
Yeah.
A good period of seeing earlier this past, actually towards the end of September. And then I was hoping for Jupiter, and the scene deteriorated quite a bit over a few hours since I took the Saturn pic, but I was able to see the shadow cast by Europa on a planetary disk, and that was kind of neat. My little dwarf 2 grabbed this image of the waxing gibbous moon at the Skull Barbecue. And this is the harvest moon rising over Halifax Harbor. And the partial lunar eclipse also captured with my dwarf 2. So this is pre-eclipse, this is the penumbral phase, and here's the maximum coverage of the moon by the Earth's shadow. And Perseus double cluster. Blair McDonald sent me a few nice pictures. This is a wide field view of the Lagoon Nebula. And you can also see the Trifid Nebula in this particular image, and a open star cluster, Webb's Cross. And all the dust clouds in the Milky Way highlighted nicely in this image. Bernard 169 and 174. So these are dark nebulae, imaged by Blair McDonald. And the Tulip Nebula, Sharpless 2101. John McPhee, waxing gibbous moon on the 15th. And John's image of the partial lunar eclipse. And a nice shot of the crescent moon with Venus for Halifax. And lastly, we come to some pictures from Kathy Walker. She's been doing some imaging of open star clusters. This is NGC 6871. The Wild Duck Cluster, Messier 11. The Cooling Tower Cluster, Messier 29. Someone with imagination thinks that looks like a water cooling tower. And a couple nebula from Kathy. So the Small Dumbbell Nebula, Messier 76. And the Heart of the Heart Nebula. Heart Nebula is IC 1805. And this is the star forming region in that particular emission nebula. And I'll just end by reminding everyone of the Astro Imaging Contest. The deadline for submissions is coming up, midnight, the 11th of November. And any RASC Halifax Center member can submit, as well as any person residing in Nova Scotia. There are 3 categories: Wide Field, Solar System, and Deep Sky, and a People's Choice Award. And with that, I'll stop.
All right, well, thank you very much for coming. Thank you for the nice introduction. It was, like I said, I've been coming here quite a lot, and for the last, I'm not doing the math, I've been here several times. I always enjoy coming here. It's always a great reception, and you guys are really interested in hearing about X-ray astronomy, which is great, and black holes and all that stuff that really interests me. So today I would like to talk to you about a new mission that I've been working on for quite some time, and it's heading for its 13th month anniversary in a couple of days, and that's the XRISM X-ray Observatory. XRISM, the X is a CR. I love X's, but this XRISM, and it does stand for something X-ray imaging spectroscopic mission.
Yeah.
So you're used to looking at the sky like this, right? This is one of the hopefully great view that we get from Stargaze, Nova Scotia, where you can see the Milky Way, optical astronomy. This is what we perfectly tuned to what our eyes can see, right? When we're looking in the optical sky, we see all the stars in the galaxy, all the planetary nebula and supernova remnants, and all that stuff that gets formed through stellar processes. And we can also see a little bit farther and see a few galaxies and things of that nature. but the optical band, what we can see is such a tiny part. Let me change the slide. It's such a tiny part of the entire electromagnetic spectrum. So the electromagnetic spectrum, just a fancy word for light. So when we're talking about the lowest energy of light, those are radio waves. Those are the things that transmit signals across the Earth and space and down to Earth and so forth, up to the most highest energy light, which is our X-rays and gamma rays, things that you see at the doctor's office. So this is all just light. It's all of the same nature. And the optical band that we've been doing astronomy with the past couple thousand years, looking at the sky, is this very small, tiny little slit somewhere in the middle. You see all the colors from blue up to red. So a very narrow part of the spectrum. The universe is radiating at all these energies. Covers the entire radio all the way up to gamma rays. And today I'd like to talk to you a little bit about these high energy X-rays. And where else, best place to start is to demonstrate that X-rays are important, that we are seeing X-rays everywhere in the universe, including very close to home. This is an image of the Earth and the aurora shining in X-rays. And we're going to see auroras are predicted to be really high with this recent solar activity that we're getting. So tomorrow should be a peak aurora activity, and we're starting to see some X-ray emission enhancement of that as well. Slide. This one of your favorite objects, any guesses of what this might be? No, you don't get to answer. Hercules cluster. Mars.
Ah,
When you look at Mars in optical light, you're seeing sunlight, which is reflecting off of the surface of Mars and coming back at us. That's how we see the planets. They don't emit optical light themselves, but it's all reflected sunlight. When we're looking at the X-rays, what we're actually seeing is the solar wind, those charged particles from the sun, which are crashing into the upper atmosphere, even the surface of Mars itself, and shining in X-rays. So we're learning about our own solar system and how the sun is operating, how it interacts with the planets when we're looking at an X-ray vision. The sun is an X-ray source itself. And as you see here, the blue and the green are the X-ray parts. You see that it's not isotropic and just kind of smoothly distributed, but it actually isn't spots. There are hot spots on the sun that emit the high energy X-rays. And also in this kind of outer atmosphere, you see that it's an X-ray source. And this is highly variable. Next slide, please. So we see that the X-rays will vary significantly over the solar cycle of the sun. And we're heading into a solar maximum pretty soon. We're going to see lots of solar X-rays or X-ray emission in the sun. But this also changes on hourly scales. That flare that went off, that coronal emission injection that went off, is going to be creating lots of X-rays as well. So this is the very first image of a comet taken in X-rays, going all the way back to 1996 with a telescope called ROSAT, German telescope called ROSAT. What was really surprising about this is, like, here's this chunk of ice about the size of a mountain going around the sun, but it's actually as bright as Jupiter's in the X-rays. So even though it's just a little tiny rock in comparison to Jupiter, it is extremely bright in the X-rays. And you see that this is also something that has to do with the sun, as it's kind of bright on the sun side and not emitting any X-rays on the dark side.
Is that caused by the emissions of the, like the cold?
This is one of my favorite ones. This is an X-ray image. The blue actually kind of extends over the whole part, but you don't actually see it all. But this just shows so much structure. You have this very extended blue diffuse X-ray emission. You see that you have a very compact source at the center. You have rings of material. And if we can just look at the time lapse, you can see that that's actually changing with time. So that's actually material which is moving. And you even see some jets coming out of this compact source. Before I show you the optical, is there any guesses on what this would be?
M1.
M1. Or what kind of object is it? So so it's your optical image. If you put it together, put the X-rays on top, it's your Crab Nebula. Yes. And the center, that point source at the center is your pulsar. This is the remnant of the star that has gone supernova. And material which is ejected upwards. And the reason that the Crab Nebula is still shining today is probably because of all this material which is being ejected out from the pulsar at the very center. So that's kind of like rejuvenating the supernova. Okay. These ones, these are some of your favorite objects. But all right, they're all the same type of object, but looking at them in the X-rays, you see that they have very, very different appearances. So you have some compact sources, some spherical, some elongated, some messy. Any guesses what these are? Like looking.
Hmm.
Yeah. Nebula.
Yeah.
Dumbbell and that sort of.
Yeah, planetary nebula. So there it is in the optical, and if you overlay the images, there are the X-rays. The X-rays are coming from the most compact regions. So when planetary nebula form, they eject material, and they do this. They eject material, and then they stop for a bit, and then they eject more material. And the stuff that's closest to that very center star, that white dwarf or star which is aging, is where the X-rays are coming from. So they're coming from the very closest inner region of the planetary nebula. This one is also a really cool image. You see that you have a lot of structure here, lots of diffuse material, and then some compact, complicated structure, which we'll zoom in a minute. But any guesses what this one is? You get to see your answer again.
Oh, galaxy.
Oh, awesome. This is a colliding galaxy called NGC 6240. Two galaxies which are colliding together. You see the stars and the dust and all that. Next one, overlaid with the X-rays, and you see where the X-rays are. X-rays are this entire huge region. This is gas which is being ejected from the central region, and eventually it might actually cool again and then fall back in on the galaxy and form stars again. So this is actually a very active star forming galaxy. If we zoom into the very center, there we go. We see this is still X-rays, but this is just highlighting low energy X-rays in red, and the blue is the high energy X-rays. And you have 2 points there. And those are two supermassive black holes which are merging together in the very center of this galaxy. So each one of those galaxies had its own black hole at the center. It's now crashing into each other, colliding, forming a single galaxy. And the black holes are somehow managing to find each other and migrate to the center to form one giant, eventually to form one giant black hole at the center of the new galaxy.
What is their distance at this point?
Separation. We don't know exactly because we don't have the. But it's going to be a long time. These will eventually form gravitational wave. Certainly not in our lifetime, but these are the types of objects that we'll be seeing with the conditions that are sort of regions. So the same thing if you don't. It's great. So talking about black holes, pointing out that black holes are to X-ray astronomers what stars are to optical astronomers. I showed one of the second image I showed was that Milky Way and all the stars distributed across the sky. When you look at that swath of sky in X-rays, you're seeing individual black holes all across the sky. This is actually a piece of sky in the Moody's cluster and the moon to scale. So a big, large piece of sky, and those are all black holes. So you see one of them. And the color is giving us an idea of the image or the energy of the black hole. This is also one of my favorite images. This is a cluster of galaxies. Okay, so these are hundreds of thousands of galaxies, which are all gravitationally bound. They're all moving around each other as a single unit kind of thing. Biggest, largest gravitational bound structures in the universe. Okay, I'm going to overlay the X-rays now. This is an optical image, and this is what the X-rays look like. Okay, so this is 10 million degree gas, 10 million degrees Celsius, and it is filling the space between the galaxies. Now, why is this important? This gas, very hot extreme gas, as diffuse as it is actually about 5 to 10 times more massive than all the stars in all the galaxies that were there. Most of the matter emitting light in the universe is in this form, is X-ray gas. It's very hot gas. So if we want to understand most of the material in the universe looks like, we need to understand what's going on at very highest energies. So this brings us to XRISM. All those images have been collected over, I think the first one I said was from the 90s. Several telescopes, ROSAT, XMM, Newton, Chandra. I think there was even a Saskatchewan mentioned there. This is our newest toy. This is XRISM.
Right.
So XRISM was launched September 2023, September 7th, so 13 months and a couple of days. And from the Tanegashima Space Center in southern Japan, one of the islands of the southern coast of Japan. And this is a huge collaboration led by the Japanese Space Agency, JAXA, in collaboration with NASA. ESA is also involved, and we do actually have some Canadian involvement as well. And next slide. There we are, St. Mary's University labeled there. I made that big. And we actually had a contribution to the next slide, please. We did make a contribution in that we were involved in the calibration of the filters that go on the telescope. And I'll explain how that works later. But this was work that was done at the Canadian Light Source in Saskatchewan in February. So I have to point that out because you aren't quite as fine for being in Saskatchewan in February. Next slide, please. Some mission specs. This is a really big telescope. It's 8 meters from the top to the bottom. The top plate, I'll explain, I'll show the instrument set of 8 to the bottom, and the solar panels extend about 9 meters across. It is built for a design to have a lifetime of 3 years. We're most likely going to be hitting at least 5 years, and the instruments can actually be operated in such a way that it could go on for even much longer, about twice as long as that. So as long as everything stays healthy and we start continuing to do good science with it, we might go up to 10 years with this telescope. So, and it's in a low Earth orbit, so it has about an hour and a half. So as I was mentioning, I call this an observatory as opposed to a telescope because it actually has 2 telescopes on it. In the top plate, we have 2 telescopes. They're identical. I'll explain how they look like. We call this the X-ray mirror assembly, XMA. One of the telescope focuses X-ray light to a detector, which is a CCD imaging detector, which we call extent. And the other telescope focuses X-ray light to the main instrument on the telescope, and we'll show you why that is. This is an X-ray spectrometer called Resolve. Okay. So all this kind of works together to produce kind of like really high accuracy images with very high resolution spectroscopy. And I'll explain what those mean in a second. So I want to go through the different components, the X-ray mirrors, and then each of the detectors. The X-ray mirror assembly, the kind of design that we use to focus X-rays is called Ultra 1 design. The point here is that you can't design X-ray telescopes like you design optical telescopes. So optical telescopes, you have a mirror, some curved surface to it, spherical, parabolic, whatever, and you have the rays of light coming in perpendicular to your reflecting area, and they get reflected and brought to focus at some point. Can't do that with X-rays, right? If you do that with an X-ray telescope, the X-rays are just going to penetrate right through your mirror, or they're going to get reflected off in some arbitrary direction that you don't know, have no control over where they're going. The only way we can actually focus X-rays, high energy photons, is to do it at what we call grazing incident optics, grazing incident angles. You have to skim it at very shallow angles. So the analogy I use is skimming a stone across a lake. Right. So if I take the stone, that would be my photon, and I just drop it, X-ray photon, and just drop it, it's just going to crash into the lake. If I want to give it some direction and send it into a preferred direction, I have to kind of skim it at a very shallow angle. So we take our mirror, we build our mirror, and then we tilt it pretty much parallel to the light ray coming in. So it's really hard to collect photons. So we're not really building a mirror per se, but we're building shells. And so we build these shells, the photons come in, graze in, and get focused. Okay. And this design in particular, and you see that we kind of nest the shells together. And this design in particular requires that you have two reflecting surfaces. So you come in, you reflect off one set of shells, and then the X-ray reflects off another set of shells, and then it comes to focus wherever you have the detector. So you build segments and put these mirrors together. So it's not building a single mirror, but you build all these segments. Can you see that? So you have all these little segments that will eventually make up the entire ring, the entire shell. Okay. There's about 1,600 segments, more than 1,600 segments in each one of the mirrors. So you have build these segments through the mold, and then you kind of insert them. You build it by quadrant. So you build a quadrant of the mirror, and then you stack them together. So I don't know if you can see it so well here, but you basically have, here's one quadrant from one reflecting surface. So that would be an outer reflecting surface. And then you stack it on top of the second reflecting surface, which is here. Build them in quadrants, and then you align them all together and calibrate them and make sure it's solid. Next slide, please.
What's the radial separation between those segments?
So, I mean, this might help do the math.
Okay.
It's 203 shells in there.
Yeah.
And 45 centimeter diameter. Okay. So these are small. They, for a couple of reasons, they're really heavy. So you can't really build them that big. And you can imagine how it is to align 200 shells. And so there's a lot of work to do that. So you are really limited in how big you can make these things. And how much time you have to build them. And this is just like showing one of the mirrors kind of, you remember this is located on the top plate of that satellite, which is 8 meters high. So you lift it up by crane. And this is the installation of the mirror. It looks like this one. This is the one that points to extend. It's already been installed, and now they're looking. Looks like this where they're installing the telescope for the resolve instrument. So one of the detectors is called Extend. It is a imaging detector. It's not unlike ones that we have used already. They're CCD detectors. You can see them here. There's actually 4 of them that are put together to create a mosaic. But and it's operating in this energy range between 0.4 and 13 kV electron volts. What was interesting about this one is that it has a really huge field of view. Really huge for us in X-ray astronomy. So 38 square arc units. So if you change, next slide, please. This is an example. This is one of the first light images that we have with the detector. The optical images are shown in the background. Okay, and this is the footprint from the XRISM, that big white square, and compared to other telescopes. This is one of the clusters, Abel 2319. This is that hot gas that kind of looks between galaxies. Okay, and you can kind of see just the amount of extra space you have on an energy bit on this detector compared to other ones that are before. The next image, supernova remnant 1006. These are all just beautiful to look at. This is really kind of raw data. This hasn't been processed, but just to kind of show you again how much of the sky this supernova remnant is taking up. We can actually get the entire thing just by with one image with Extend.
Are you able to, I know with visual, they have sometimes they trace the gas between 2 galaxies that are beginning to merge. Be able to do that with this?
Yeah.
See the.
Oh yeah. I'll actually talk about moving gas in a couple minutes. All right. The main instrument on board is a microcalorimeter called Resolve. And I'll try to describe what a microcalorimeter does. Basically, it produces ultra precise energy measurements. Next slide. See, this is what I have to do perfectly, right? Ultra precise energy measurement. What does that mean? I thought it was kind of dumb when I first wrote it, ultra precise energy measurement. But it's actually It makes sense. Okay, so what do I mean by energy measurement and ultra precise energy measurement? Basically, what I'm talking about is spectral resolution. So spectral and energy being the same thing here, spectral resolution. You all know what spatial resolution is, right? The ability to distinguish two objects that are close together. Right. So with your telescope, you're always trying to get better spatial resolution. Again, analogy I use is waiting at a bus stop at night and you look down the street and you see some light coming towards you. At a very large distance, that light is a single light. Can't tell if it's a motorcycle or if it's a car or if it's a big square front of the bus. Okay. As it comes closer to you, you start seeing the headlights separate. And if you're a fan of HRM bus system, you'll be hopeful that it's a bus. But as it gets closer, you can distinguish it as being a car, a bus, or a motorcycle. And in optical astronomy, this is a factor that depends on the size of your telescope. And but you're limited by your sky. So your sky creating the scene, the vibrations in the earth. So your telescope is much better than the sky allows you. So with a small telescope, you can actually achieve very good spatial resolution. Energy resolution or spectral resolution is the ability to distinguish features within light. So what do we mean by that? Like I have to define three terms here and describe that. The first one is spectroscopy. Okay, so spectroscopy is just the study of the components that make up light. We are all familiar with this. You know, when you let sunlight or you put a flashlight through a prism, you see it kind of break up in all the different colors. Those are all the components that make up light. So white light is not something that is intrinsically pure. It is made up of all the different rainbow of light. So being able to look at those distinct colors and seeing which ones make up different. So like, and you may have done this exercise when you're in high school or first year university where you had like a gas-filled lamp. You send a current through it and it excites the gas in there. And you look at that through some sort of telescope and you see that it emits a pattern of light at very specific colors. By looking at that light and identifying that pattern, you're able to identify what makes up what that gas is made up of, what the composition of that gas is. Right. So you get a neon light produces a very distinct pattern compared to a sodium. So that's spectroscopy. Your spectrometer is just the instrument that separates the light into its components. So your prism is just your spectrometer. You can get more fancy, and that's what the result is. It's probably the most fancy kind of spectrometer you'll ever see. And the spectral resolution is just your ability to distinguish those different components. You have very high spectral resolution where you can see all the individual features, or you have fairly low spectral resolution where you just see this kind of swath of light just changing in color gradually. You can't really distinguish what one color ends and another one starts. So just kind of hammering the definition, spectral resolution. This is an example of looking at sunlight with low spectral resolution. Our spectrometer is just a raindrop. Okay, sunlight going through the raindrop produces our rainbow. Very low resolution solar spectrum. You go up a notch and you perhaps use a more better spectrometer, and you can kind of see that you start identifying different features in there. Okay, so this is the exact same range of color that you see in the rainbow, the exact same range. But you start seeing individual components. You see that some colors are brighter than other colors, and you see that there's actually some colors that are missing in that. Okay. If I go to the very highest, again, this is the exact same energy range, light going from violet up to red, and you see that at the very highest resolution, you see all the different components that make up that light. And the same thing is being used in X-rays. So this is the spectrum. These are all the same object, Cas A, supernova remnant. We're looking at it with low resolution, and you see that you can't really tell that there's actually any features in there. We increase the resolution slightly, you start seeing, oh, there are things that are starting to pop up. and you increase it even higher, and you start seeing even narrower features and different strengths. So we're trying to increase our spectral resolution in this case. XRISM, the resolve instrument of XRISM, is a microcalorimeter, and probably the most advanced kind of technology that we have for creating spectra. What this is doing, rather than kind of having a prism that separates the light, what this is actually doing is measuring the temperature of that photon that comes in. So by measuring the change, the photon will come in, the X-ray photon will strike the detector, it will raise the temperature of the detector by a certain amount, which depends on the energy of the X-ray photon. So you can imagine the higher the energy of the X-ray photon, the more the temperature change is. And we can measure this temperature change and make a spectrum out of that. Now, show you the detector comparison size. Next slide. That's how big it is, 5 square millimeters for that detector. Now you can imagine these temperature changes that we're trying to measure are very tiny. We're like talking about like millikelvin levels. Okay, we're trying to measure this. We need to keep this detector cool at about 50 millikelvin. So near absolute zero. So minus 272.5 Kelvin or Celsius, sorry. That's how cold we have to keep this detector. So this little 5 square millimeter instrument detector slide needs this entire thing to keep it cool. This is what we call the doer. Basically just your thermos that you try to keep it cold at. And this is a feat in itself. The detector is amazing, obviously. It gets all the credit, but this thing is such a challenge that in the past, we've actually had failures with this that have failed the mission. And the detector's fine. So this is most of the work actually, I shouldn't say that. A lot of the work goes into actually creating this newer system compared to the actual detector itself. But is it worth it? I certainly think so. This is one of the first light images taken, first spectrum with resolve. This is an image of another cluster called Perseus, and this is the high resolution spectrum. If I zoom into this very narrow region, this is actually emission, those bright lines that we see in the spectrum created by iron. Okay, so just zooming into this section here. It's kind of easy for me to sit here and say, wow, this is amazing. You're like, whatever. Okay, let me show you what the best previous spectrum looked like. That's the blue one. That was our best spectrum before this. And now we're actually able to see all these different features coming in. So we have several different emission lines. And why is it important to do this? Why with accurate spectroscopy, we're learning all kinds of physics about what's going on in that gas. The image is beautiful, obviously, but now we can actually get information about the temperatures, the pressures, the chemical composition, and the composition, the dynamics. How is it moving? Is it blowing outwards? Is it falling inwards? Is it moving around in a circle? What is it that it's actually doing? We learn all that from the spectroscopy. So, what's going on up to date? As I said, we launched it almost exactly 13 months ago. The first 3 months of the operation, so basically most of 2023, it was in a commissioning phase. So the telescope was all the instruments were being tested and making sure that everything was healthy and working properly. In January of 2024, this year, we basically started what's called performance verification. And that is making observations of science targets. And these targets will be analyzed specifically by the science team. We did this for a 9-month period. Now, the reason we want to do that, we get dibs on the really exciting stuff, and we get to look at it first. But it's also an opportunity to actually test how the telescope is working and figure out how we can use the data that's coming from the telescope so that we can tell other people in the community, so they don't have to actually learn everything from scratch. We were supposedly the experts. We then are able to explain to them how to use the data that they're collecting. So we did this for the first 9 months. of, since the beginning of the year, ended August 31st. We made observations, 70 different observations of all types of objects, supernovae, active, black holes, stellar mass black holes, supermassive black holes, pulsars, cataclysmic variables, all types of objects. And since September 1st, we've been operating in kind of the guest observer mode where we let the rest of the use the telescope. So we're at a position where we've been working on data. A lot of us have been working on data for about 9 months now. We're just starting to kind of get the science results. So I'd like to talk to you about a couple of the science results that we have so far. The first one is of this supernova called M132D. Okay, so this is the supernova remnant. The explosion from the star was about 8,000 years ago. I said that wrong, 3,000 years ago. And this is located in the large fatty line cloud. So this is the X-ray image that we're seeing right here. And this is the spectrum that we get from result. And just highlighting in the gray line in the background, that is the best previous spectrum that we had for this supernova remnant. So just in comparison, you obviously there's nowhere near as much information that you see. So maybe before I go farther, I just want to explain a little bit of how a supernova is actually formed. When a really big star starts to run out of fuel, just before it kind of runs out of fuel, it starts losing its outer shells. Okay, so material starts to dissipate out into space, kind of like planetary nebulae and so forth, and material starts going outwards. Eventually, that's going to be happening for millions of years or so, something like that. Eventually, at the very core, that star will run out of fuel. And when it does, when that core kind of runs out, isn't burning, isn't creating any more energy, what happens is it starts to fall in on itself. As it falls in on itself at the core, it gets to a point where it can't fall in any farther and it explodes upwards, and that's your supernova. Now, in doing that outward blowout like that, it creates a shock wave, which then moves very fastly throughout the entire star, and actually even starts to catch up to that material that it had been traveling for millions of years beforehand. This pulse, this shock, has so much energy that it heats up that material around it as it's passing through it, heats up this material up to X-ray temperatures. And you can imagine that, you know, as it goes farther and farther, it starts to lose energy, starts to dissipate it, and then it will heat it up to maybe instead of X-ray temperatures, it will be optical temperatures, radio temperatures, and so forth. So it kind of cools as it goes over. The region closest to the explosion itself will be very X-ray hot. So that's how these work. If we take a spectrum of this now, we'll start pointing out some of the neat stuff that's going on here.
Just before you go on, that's the spectral resolution. What is the spatial resolution with
Spatial
respect?
resolution isn't that great. And better. I think spatial resolution we're talking about less than working. Yeah. So the spatial resolution, like I said, wasn't intended to be the prime driver of this. It was the calorimeter itself. So here we are focusing on the spectrum itself. And what I want to point out here is that this is that line coming from iron, and you see that it has some width to it. But if you look at the other lines, they're all identified here, but these are mostly silicon and sulfur and argon and things like that. You see that they're actually much narrower. Okay, so these ones are narrow, but this one is actually kind of fat. What's happening there, the way you kind of create this fat line, is by having all that material, having that iron material moving really fast. The faster the material moves, starts banging into each other and starts moving in all these directions, it creates a broader line. So how wide your line is dictates how fast the material which is emitting it is moving. So we see that the iron line is actually moving really fast. And these ones, these silicon and sulfur lines are moving slower, much slower. This dictates they're moving slow because the temperature is lower. Okay, so atoms move much faster when the temperature is high than when the temperature is low. This iron is being created very close to the central region. And it is, what is that? 10 billion. It's ridiculous. Doesn't even matter what units we're using. It's all the same. It's 10 billion. It's hot. And then the stuff coming from this stuff is happening farther out, and it's at around 10 billion. So what we're actually seeing for the first time is we're actually starting to measure that temperature gradient that I was mentioning to you about words, and we actually see the otter stuff closer. Now we can actually see it right directly in the XRISM itself. Another observation that we have is of a supermassive black hole at the center of this galaxy called AGC 4151, fairly nearby, 52 million light years. Maybe you've seen it yourself. It has a supermassive black hole that is 30 million times more massive than the sun. And that's about even 10 times more massive than the black hole in our galaxy. So it's actually relatively small in terms of supermassive black holes, but pretty big in comparison to the stuff really close to us. And what's interesting about this system is that that central black hole is extremely active. And it's what we call an active galactic nucleus. So making an observation, what I mean by active galactic nucleus, you produce a lot of energy. The supermassive black hole will produce a lot of energy when you have material which is falling up towards it. Now, how we actually are able to figure out how this material falls onto the black hole is an unknown. This region is tiny in comparison. This entire region is probably the size of the solar system, or this inner region is the size of the solar system. So understanding that and being able to see that is near impossible. It's impossible. So we really rely on indirect methods like studying the spectrum of this. But what we think is happening is we think that material kind of like starts at these very large scales and kind of funnels in down towards the black hole. And as it's doing that, it starts moving faster and faster and faster. So the stuff on the outside is moving fairly slow, and the stuff very close to it is moving extremely fast. So I'm going to take a cross section of this. So just imagine cutting this in half. Looking at the side of it, that's what the result is that we're going to show you. So this is the spectrum. This is again that iron line that we were talking about. But what we were able to do with this observation was that we were able to break this iron line and find the different components. There's actually emission coming from three different parts of this region that go into that one iron. We have the narrow part shown in pink, which is coming from this region very far away. Okay, that's cooler material. It's moving slower, as I just kind of in, right? And then you have slightly broader, which is coming from a region slightly closer. And then as you get very close to the black hole, you have part that's actually extremely broad like this. Very shallow, but it's very across the extreme region. So we're actually able to see where the iron is coming from three different regions in the black hole. And also to highlight that this is work that we've actually had St. Mary students on. Margaret in the back there, who's actually one of the co-authors on this paper. And she's got her laptop up and she's actually writing another paper right now. That's interesting data. So yeah, so just to highlight like this is opportunity for students at St. Mary's to be involved on this work. So just to wrap things up, we're just starting to kind of get the data out. These are the only two data sets that I could actually really talk about at the moment. We have a lot of results that are been submitted for publication, and just lots and lots more stuff to come. And have it come back in a year or so to talk about more stuff. I want to highlight that XRISM is really kind of revolutionizing what we know about the hot universe. The hot universe being things that are every day in our own backyard and on the solar system, even at the Earth itself, but across the entire universe, and contributing to a significant part of our understanding. And we really are kind of going into this uncharted territory with this new detector called Resolve. We're looking at this very high resolution spectral resolution, and yeah, Canada and St. Mary's in particular is able to be at the forefront of this, taking part in these new discoveries. Thank you.
I'm sure we're all excited about going where no person has gone before and where you take us. And yes, we will have you back. And I won't be here next time. Any questions from the room or from anyone out in Zoom land? One here, Jerry?
I've got a question about the previous slide here. The line that you show for the accretion disk doesn't look to be particularly visible as to what's going on there. That's a pretty flat curve.
Yeah, because I'm not showing a lot of things here. The spectrum itself is actually, go forward to see if I actually have a backup slide.
Keep going.
Oh, more. Okay, so these are the actual data. Sometimes, the public image is actually not as good as the real data. This is actually covering a region, like what I was showing you was this basically tiny region. That was what was in the cartoon. This is what the real data looked like. This isn't all the real data. This is only one observation. We actually had 4 observations and we put all the data together. It actually showing again 5 to 9, but we actually have data going all the way down to 2K read. This actually goes up to about 12. So I'm still not showing you all the data. But what you start to do is once you actually fill that in, we call it the continuum, which is basically the thing that covers most of the stuff. And we actually find that this might be representative of the continuum here. And that wide shoulder is actually a bit more significant than it actually looks in that cartoon. So I actually will say that the real data, lots of times we don't want to show the real data because it's scary. But this is probably an example of the real data that looks better than the cartoon.
That's the data we give students.
Yeah.
Any other questions here or in Zoom land?
I'm a X-ray astronomy neophyte to the extreme, but why is it that XRISM is like? What are the benefits of having an orbital telescope, X-ray telescope, as compared with like ground-based?
Oh, because firstly for X-ray astronomy, X-rays don't penetrate the atmosphere, so we can't do the X-ray astronomy from the ground simply because X-rays won't penetrate the atmosphere, which is a good thing. So we're happy with where you put the orbit, where you put your telescope depends on a lot of factors. Money being a huge one. For example, JWST is out in altitude because you put a lot of money into actually sending it that far. So it's also a budgetary reason. It also is. There's also how another reason driving it is how sturdy you have to build your detectors. So being in low Earth orbit, you're actually protected by the sphere of the Earth. Being at a large distance, a lot of telescopes get to a large distance where they're exposed to solar radiation and all that sort of stuff like that, and they have to be built much harder. So it is adding a lot of weight and a lot of money. So there is some thought into why you're putting things in certain places. Money is a driving factor, and how sturdy you have to build your detectors.
Question?
Carrying on with everybody, you mentioned that the project was 3 years, yet it could go to 10. So is it inherently going to last for 10 years? It's just a matter of how many resources you have to utilize it, or what? Because it seems to me that something's going to last 10 years and it'll be a whole lot more expensive than 3. But maybe that's not true. So
you build a telescope. When you kind of design the telescope and you build it and you sell it as to the funding agencies, you kind of state the minimum requirements. We need this telescope to run with 3 years. With 3 years, we are going to satisfy these science goals and all that. So you design the telescope, you design the instruments to make sure that they live that long. What we're kind of saying is a lot of these telescopes can probably live a lot longer if they're allowed to. Now, every year you go through a review process where the agencies, NASA, JAXA, and so forth, will kind of see, are people using this telescope? Is it still being of interest and so forth? We get 10 times oversubscribed, meaning the community, we have 10 times as many applications that actually get accepted. Yeah, the community is pretty interested in it. And as long as things like that is happening, even in 10 years, nobody's going to turn off your telescope. So we have an example, for example, Chandra, which is an X-ray telescope from NASA, and XMM, which is an X-ray telescope from Europe. They were built for a 5-year lifetime in 1999, and they are still operating because people are still using them. Working backwards, sorry.
You're looking at iron spectrum. Are we looking at iron specifically because it has the broadest line, or is there a different reason for that?
Very good to notice that we are focusing on. It's very.
Next on our agenda is a gentleman I always love introducing. I always refer to him as our resident poet. Paul Heath, at all of our meetings, presents a wonderful poem for us to enjoy. And so, Paul, longtime member and poet, come forward, please.
I haven't been out for a while. As you can see, it's getting harder to get around. But
Just a second here. Paul. I hope that's going everywhere.
I centered or both tools.
You don't have your image, so we'll have to go without that.
That's not the picture, but it's perfect because it has all the things I described in the poem. Worked
Okay.
out good. Now, this one's not a very long one, but it was the morning before the partial eclipse, and I get off work about between 6 and 7, so just around sunrise. So I worked from 1 in the morning. So this was a amazing sight, just an amazing sight coming up the hill into Dartmouth. And, a glorious rising. The sun today, in glorious brilliance, a huge burning orange-red orb, rising above a thin line of midnight cloud. Gray clouds above reflecting its striking hue. It held one's eye. A perfect flaming sphere, solitary upon the distant pale blue sky behind. Its majesty shrinking to the eye. As it rose above the midnight cloud, the gray cloud shedding tears now at the loss of its brilliant attire. And through the scattered drops it paled, an ember colored orb now lost upon the closing sky. Perhaps unseen behind, a rainbow briefly declared its glorious rise. The cloud wept openly now, as its shrinking gray was lit in the promised golden light. It was amazing. Sometimes sunrises and sunsets just hit you. And after working on like lugging boxes, it was like I come up the highway and there it was just like full in the sky. It was amazing sight. And then the eclipse the next night. So it was amazing to see.
That picture, by the way, is one of Jerry's And it's of sunrise on Second Lake in Lower Sackville. Thanks, Paul, so much for that. As always, it gives you one to think about and to enjoy that glorious rising. Next up is our president, Tony McGrath. There is a lot going on in the center, and Tony will address some of what is going on. So, Tony?
Thank you, Judy. Just a couple of items. One I'm very happy to announce was that, as some of you may know, the center was received from Jane and Alfred Howard a donation which consisted of a Celestron H 200mm H HD telescope and a hyperstar setup and an ADI camera. Our own Jerry Black recognized the potential of this equipment and had spent some time getting it commissioned and up for operation, and it is now functioning. And Jerry gave me a little bit of an introduction to it at the St. Croix barbecue, and I think it's going to become one of the treasures of the Halifax Center. The equipment effectively reduces or eliminates all the hurdles to someone who's interested in some astrophysics. For the absolute price of zero, you can have some fun and learn some things. So if you want to go to the observing web or to the RASC website and click on the observing tab and go down to the bottom of the page, we'll see a K-Star automation link. Just click on it. There's some introductory information there about the telescope itself. It really is quite amazing. It's an instrument that operates at f1.9, so it's capable of some pretty short exposures, and you can get some. And in fact, we've seen some of the results. You've probably seen on the list that Jerry has posted that have been done with that setup. So it's available for use. Documentation is in process. It's done. There's documentation there, but it's one of those things where it needs to be read a few times by someone who didn't write it to be sure that it's completely clear. So that's a working process. And if you want any information about any of that or to get started, reach out to Jerry's made himself available, or in fact, or myself, and we'll point you in the right direction and get you started. So very happy about that, Jerry. Thank you. The only other item I wanted to mention was volunteering. I encourage folks and anybody who's listening or here to consider volunteering for the center. There's a couple of opportunities available. Actually, one is at a national level. There's a board. The director has had to resign his position, and so there's a vacancy on the national board. So if somebody's interested in volunteering at that, let myself or Judy know, and we'll point you in the right direction in terms of who you contact. And as well, of course, we're into October now, so December is the end of the year for this particular board of directors. So if anybody's interested in participating at the board of directors as a volunteer, again, reach out to myself or Judy, or in fact, anybody on the board. We'd be happy to chat with you. I'd also encourage everybody, if you have a chance, to look at our Halifax 2024 plan. There's a bunch of things in there. Very happy. Love to get some feedback from people on that. And again, if anybody is interested in doing some volunteering, reach out and let us know. And if there's anything in that plan that strikes you as something you'd be interested in doing, let us know as well, because we hope to get started with some workshops in the later fall or that kind of thing. So again, appreciate the help we can get. So it's right now, it's not on the website, but I will put it on the website. It was mailed out to all the membership. You may not, Tiffany, you may not have gotten it, but we'll put it up on the website so that it's available there. Yep. Yes, ma'am.
Yeah, weather station. For scope, there was some talk on that distribution of developing a weather station.
Yes.
And I had sent some information out with regards to providing an RF link.
Yes.
That we give you everything you need. Was there any movement forward on that?
We actually discussed it at the last meeting, and we're just in the process of collating what was decided. So we'll be in touch with you shortly about that.
Okay, good.
Yeah.
Because once again, I can get that information. I've already spoken to the Nova Scotia Amateur Radio Association, and we can get all the equipment we need for free. Everything from the end of the antenna where it transmits out to the computer that'll be used to put the packets together of information. So
okay, thanks. Yeah, we'll be in touch shortly. Yeah. Thank you, Judy.
Thanks, Tony. I'm just gonna add one thing, with respect to governance. Which is, for those of you that know me, know that I really do love policies and I don't know why. Our governance review committee, comprising Pat Kelly, Greg Dill, and myself, reviewed all the policies, all the position descriptions. They've been approved by the board. They are now, all the upgrades are on the website. But the biggest piece of the puzzle, of course, is having reviewed them, how did they affect our bylaw number 1? And you will be hearing from us at the beginning of November as to what changes to bylaw number 1 will be. They aren't major, but trust me, but they will be coming. So just to give you a heads up. Next up, more exciting than bylaw review, is our David, again, Dave Hoskin, with the What's Up for October. And just so you know, it is already posted on our website as of October 1st. So if something screws up with this particular audio and presentation, please know that it is on our website. So David?
Okay. Share screen. Right, is everyone seeing that? I think I see it. Okay. So what's up for October? Days are getting much shorter. We're past the equinox in September, and the start of the month, dawn started at 5:35 with sunrise after 7, and dusk ending at 8:30. So lots of 9 hours of darkness. So good times for the imagers if the weather's holds well, and that'll increase to the end of October, where we'll have 10.5 hours of darkness, with sunset at 6 and sunrise at 7:51. The typo there. So the sun has been very active. We've had 2 X-class solar flares in the past week. One was, I believe, an X9, so one of the strongest. Those flares came from sunspot group 3842, but not to be outdone, there are 2 other sunspot groups with unstable magnetic fields with the potential to unleash M or even X-class flares. So, and 3848 is just coming in line with the Earth. So if we get any flares from that guy, assuming the weather clears by the end of the week, we might get some northern lights visible. The CMEs from 3842 are due to arrive late tonight or tomorrow. Looks like the sky's going to clear late tomorrow evening, so maybe if they're later than expected, we might even get something tomorrow. New moon was on October 2nd, and today the moon was near Venus. But of course the clouds wouldn't have helped. First quarter moon is on the 10th. And just to remind you, we're in the animal fattening moon period, Kiwikus in Mi'kmaq. On the 14th, have a look for moon near Saturn. Full moon on the 17th, followed by the Orionid meteor shower on the 21st. On the 23rd, the moon will be near Mars. The 24th is the last quarter of this particular moon. So tonight, have a look in the clouds break in the west. Have a look at 7, and you'll see a very thin crescent new moon with Venus just above it. And on the 14th, this is a nice binocular target. The waxing gibbous moon will be near Saturn. And this is what you would see through 7x50 binoculars. If you're an imager, you might be able to be really nice to catch lunar surface and craters along the terminator and the ring planet nearby. And on the 23rd, looking in Gemini, you'll see the waning gibbous moon and Mars close by. Be a nice photo op if you, especially if you have a nice wide field lens. You could also get some of the DSOs in Orion, as well as some of the open clusters around Gemini and the Beehive in Cancer. But it's a challenge because you have to get up at 4 in the morning.
You have the clippers.
Anyone working on Explore the Universe? There are a number of lunar targets that you have to check off, and around the first quarter, the 15th to the 19th, that's a great time when the shadows along the terminator
One for me.
will show up nicely, and see if you can pick out 3 of these craters and 3 of the mare.
Nope.
In the montage, I showed some pictures of the comet C2023A3,
Did you?
which will be making an appearance in the evening sky after October 9th. And this is, I took this image from starwalk.space. It shows the path of the comet moving through from sextans at the end of September, through Virgo and into Ophiuchus. So you can use this to guide you if we get some clear nights. And assuming the comet survives its trip around the sun, you notice how the orientation of the tail changes between the 8th and the 11th, and might get to see a nice comet, maybe as good as Neowise. This image was the comet on its way in towards the sun that I took with the Dwarf 2 at the end of June. So its tail, if you've seen any pictures taken from the southern hemisphere, the tail is already pretty spectacular. Planets, everything's visible with a bit of work this month. Mercury is very low in the west until about the middle of the month, and then it'll disappear into the sun's glare. Venus is low in the southwest after sunset. Mars is visible for most of the night, and it is brightening. And the size of the disk will be increasing as the month progresses. So there may be some, towards the end of October, chance to get some decent images of Mars. Jupiter's prominent in Taurus, rises just before midnight. Saturn is visible for most of the night in Aquarius. Uranus is visible in Taurus for most of the night, as is Neptune, which will be visible in Pisces for most of the night. So we're in planetary season, particularly in terms of Jupiter and Saturn, both being well placed for observation and imaging. Just to remind you that this is the time to see zodiacal light in the early morning, just before dawn at the start of morning twilight. The best dates are going to be the first couple weeks of October. So if you get out to a nice dark site, look to the east between 5:30 and 6, and you may see a nice pyramid of light, which is the sunlight reflecting off dust concentrated in the plane of the ecliptic. And I believe this is an optional target for Explore the Universe. Algol, the demon star, will be at its minimum on October 13th at 9:46, and then it'll brighten over the next few hours to its maximum at 2:14 in the morning. So if you don't mind staying up late, this is a good chance to see the dimming and the brightening of this particular star due to the effects of its orbital companion moving in front of the star and causing it to dim. Autumn constellations are for you through Explore the Universe program are Pegasus, Andromeda, Cassiopeia, Perseus, and Aries. And the autumn stars, the ranking from the brightest is Mirfac, and then going down the list, Hamel, Alpheratz, Algol, Shidar, Markab, and Sheraton. And these are all good stars for the skin scan alignment, and most of them are also used for the Skywatcher handset alignment. So they're good stars to learn the location of. Our autumn deep sky object is Malot 20, the Alpha Persei cluster. This is an open star cluster found in Perseus, which Mirfac is the brightest member. So have a look at that. It should be visible quite easily with binoculars. You need a wide field. So if you're trying to image it, you'll need a camera with a wider angle lens. Not super wide, but you're not going to be able to use a Matsukov or a high focal length refractor to image this particular one. And the double star for this month is Alpha 1 and Alpha 2 Capricorni in Capricornus. It's a optical double, so these stars are not gravitationally bound. They just happen to appear close together as we look towards their orientation in space. Alpha 2 Cap is also known as Algeti. It's a yellow giant star. And Alpha 1 Cap is a yellow supergiant. So the Alpha 1 has a magnitude of 4.4 and Alpha 2 of 3.7. So binocular doubles, easy to find. So you can check that off your list of Explore the Universe double stars. And that's it for what's up in the month in October. Are there any questions?
None from the room. How about Zoom land? One in the chat. Okay, no question, just comments.
Okay, great. So everyone, keep your fingers crossed for some good weather and for the comet's survival.
Thanks, David.
Okay, you're welcome.
Okay, well, I think that wraps up our program for today. Thank you all for attending. You'll certainly know in the next few days or so about when this gets posted. We'll put it through the announce list. So thank you all for attending, both here in the room as well as those out in Zoom land. And again, thank you to our guest speaker, Dr. Luigi Gallo, for bringing us a presentation that I'm sure we won't soon forget, and yes, we will invite you back. So take care and don't forget, starting at your feet, look up. The sky is open. Take care, everyone.